In this video, we'll develop the free body diagram as a physics tool and explore the normal force and the force of gravity known as weight. So we've worked with vectors and seen how to use Newton's laws of motion. Free body or force diagrams are a tool we use to connect the physical situation with the math equations we use to analyze the information and predict the outcomes. But every tool has limitations, and free body diagrams are no exception. Remember the first law, the law of inertia? That resistance to changes in motion? Well, this is determined largely by the mass of an object and where we apply the force. Remember the ball on the cart appeared to roll backward, not because it actually moved backwards, but the bottom of the ball was drawn forward by the wagon while most of the mass resisted the push. Remember that any vector has one magnitude in one direction. Force is a vector and so is acceleration. Now the second law connects these, but the force and acceleration must have the same direction, as the only mitigating factor is the scalar mass. But we have to be careful where we push in the object's center of mass. Consider pushing this block. We'll assume that its mass is uniformly distributed throughout the block. If we push the center of its mass, it accelerates in the direction of our push. However, if we move off to a corner and push, it doesn't go exactly where we intended. Now physics can deal with these off-center situations, but the math is more involved. For our purposes, we'll only consider circumstances where our force affects the center of mass. And all free body diagrams start with this center of mass. Once this is established, we draw all the vectors with relevant magnitudes and directions that are acting on the mass. Once the vectors are determined, we can use that vector property of spatial symmetry to rearrange the vectors head to tail, so we can add them and determine the vector sum, our net force. With the net force and mass, we can use Newton's second law to determine the acceleration, which can then be used to determine the object's motion. As an example, we can use these two east-west forces along with the northward force acting on this 90 kilogram mass to determine its acceleration. Before we start working with the numbers, let's establish positive and negative directions. We'll align our x-axis in the east-west direction and the y-axis with north-south. Then we'll analyze the x and y directions separately with 72 newtons from the first vector, but no contribution from F2, and a negative 36 newton addition from the third force. While in the y direction, only the second force contributes 81 newtons with nothing from the other two. So with our net force in each direction, and Pythagoras, we can find the magnitude of the net force, and we use trigonometry to find the direction of our resultant, theta. This gives us a net force of 88.6 newtons with a heading of 66 degrees north of east. Using Newton's second law with this net force and mass gives us an acceleration of 0.98 meters per second squared, heading east 66 degrees north. Now we can use these free body diagrams to analyze situations that involve what we refer to as the normal force. First, let's look at what happens with a physics textbook if we let it go. Now we know that it has mass, and we're trying this on Earth, so we know there's gravity. And of course, if this is the only force acting, it's the net force, and the book will accelerate downward. But if we take that same book and put a desk underneath it, it no longer falls. In fact, from Newton's perspective, if the acceleration is zero, then the net force must also be zero according to his second law. And that's because the desk is now pushing back against gravity. This is his third law in action. Now when the textbook rests against the desk exerts a force perpendicular to its surface. In mathematical terms, we say this force is normal to the surface, so we refer to the surface force as the normal force. Now if we get the net force from the vector sum and only gravity and the desk are acting, we can rearrange the equation to see that the normal force must be equal and opposite to the force of gravity. But what if we push down on the textbook? Still, the textbook remains motionless, and again the acceleration is zero, which means that the net force must be zero. Now gravity hasn't changed, and we've increased the downward force with our push. The only way this can happen is if the normal force reacts to the push and adjusts in response to the change in conditions. With this adjustment, this normal force is now greater than gravity. In fact, the normal force can have no relationship with gravity whatsoever. Let's look at a decorative magnet attached to a fridge. Now looking at a side view, the free body diagram for the magnet has gravity acting downward and the magnetic attraction to the fridge. But the magnet rests against the fridge, so there must be a normal force exerted by the fridge on the magnet. And since the magnet's stationary, there must be some other force preventing it from sliding down the surface. This force is called friction, and we'll look at it closely in a later video. For now, we know that the acceleration must be zero, and this is true in both the x and y directions. So here, the normal force is equal to the magnetic force between the fridge and magnet, and the friction has a magnitude equal to gravity, but in the opposite direction. Now notice that this force of gravity comes up a lot. We see it so often we have a special name for it. This is what physicists refer to as weight. And just like our textbook, if we were placed in midair, we'd fall at the same rate of 9.8 meters per second squared. Again, just like the textbook, our net force would be provided by gravity. our weight. The common method we use to determine our weight is to stand on a bathroom scale, and the scale reads out a number in kilograms. But the scale isn't actually measuring our weight. What it does measure is the amount of normal force needed to balance our force of gravity, our weight. Funny enough, the scale reads out kilograms, but this is a unit for mass and not weight. This is where that uniform acceleration due to gravity comes in. This acts like a sort of scale factor, and the display is adjusted to show the number of kilograms acted on by gravity that would have the force to balance the scale's force. A good way to see this is to measure our weight in an elevator. Every student's dream, right? Now, standing motionless in the elevator, there's no surprise. We'd see exactly what we'd see standing on our bathroom floor. But what about when we move upward at a constant speed? Well, since our velocity is uniform, our acceleration is zero, which means our net force is zero. Newton's second law shows that the scale's normal force is still equal and opposite to gravity, so our scale still reads our weight. We refer to this reading as our apparent weight. The same is true when the elevator moves down at a uniform rate. Now, things get interesting when we accelerate upward. If up is positive, then our acceleration is positive or greater than zero. In this case, the normal force provided by the elevator floor through the scale would have to be greater than the force of gravity to give an upward net force. Since the scale measures this force, we would appear to be heavier than normal. If we think of riding an elevator, we feel heavier when it starts to move up or stops our downward motion. Now let's consider accelerating downward. Here our acceleration would be negative, and the same would be true for the net force. Again, the second law allows us to deduce that the normal force would be less than our weight, so the scale would indicate a lower apparent weight than on our bathroom floor. This is why our stomach can feel a little unsettled as we start to descend or at the end of an upward trip on an elevator.